Okay, let's start. Today I'd like to share the idea of un-terminated black box modeling for electrical machines. My name is Xinliang. I'm from CPAS, and I was from China and ever finished degree from Shandong Province, South Korea, and then came to CPAS for pursuing PhD degree in power electronics. I will start from the background and concept of the so-called terminated and non-terminated terminal behavior model, and then how we experimentally extract the model, how we design the experiment, and finally the conclusion and future work. So recently there is a trend that we want to electrify complex systems like more electrified ships, more electrified aircraft, airplanes. But usually when we purchase machines from the manufacturers, usually they are not willing to disclose all of the information for the machine itself. Before installing those machines, we really need the model to do like software-based simulation, hardware-in-the-loop simulation, or real-time power hardware-in-the-loop simulation. Even if during the operation we want to predict the stability, or we want to do fault diagnostics, all of those tasks really heavily depends on the model we master in hand. So there is always a need, a bridge between the manufacturers and system integrators. While the intellectual property is still protected for the manufacturers, but we really get the information we want for those tasks. So of course, the approach would be a black box modeling, and how we do that is in the frequency domain at the, let's see the laser, at whether the electrical interface or the mechanical interface, we proactively inject some oscillation and we look at the response from the system. We try to use the ratio between the input and the response at the same frequency to represent the behavior for the system. But usually when we perturb the system is always keep connecting with the upstream electrical motor drive and downstream mechanical load. So the simple ratio between the input and the response not only contain information for the machine itself, but also upstream and downstream impact. We really want to decouple those upstream and downstream impact. So today I will show you how we theoretically have the method and do the experimental extraction. In the bottom, the blue figure shows still with the impact of the downstream or upstream, and the red line is what we want, the so-called unterminated terminal behavior model. We do have some math deductions starting from the ABC coordinates for the machine. We have a number of ordinary differential equations describing the dynamics. After using the coordinate transformation, we want to rewrite the system in a DQ frame, while the d-axis is aligned with the rotor blocks. But there are still some nonlinearities, like the product between the state variables and the model inputs. And usually we, at operating point or equilibrium point, we linearize the system, we could get the state space equation describing the system's dynamics at that point we are interested in. If the parameter is accurate, after the S-domain Laplace transformation, we could get 3x3 matrix containing 9 impedance. This is a so-called unterminated terminal behavior model, but usually the parameters is really inaccurate compared with the datasheet, especially when the current DQ-axis current is different compared with the rated operating point, then the model is not accurate. And even if the machine is not only electrical part, but also contain mechanical and magnetic part, if we following the same governing equation or the same OD equation, we transform the torque into speed, transform the torque into voltage, transform the speed into current, we could get a totally equivalent circuit describing the system, like the bottom figure shows. And this page I will totally show you why there are always some coupling from upstream and downstream. Let's assume that we want to get the impedance of YDD, so we want to perturb the D-axis voltage. The three directly related impedance or the control sources will oscillate at the same frequency, but because our source is not an ideal voltage source, the load is also not an ideal torque source. So they have internal impedance, whether mechanical internal impedance or electrical internal impedance. So they will also oscillate at the same frequency, And then all of the 9 impedance or the 9 control sources will oscillate at the same frequency. So the ratio between the input d-axis voltage and the output d-axis current is not only equal to the YDT, but also with some extra terms. Those are coming from upstream and downstream. We say it is electrical mechanical cross coupling. And what we want to do is only leave the red term, the unterminated terminal behavior model, while decouple them. How we do that? Firstly, we consecutively perturb the axis voltage, Q-axis voltage, and the torque, mechanical torque. At the same time, we could get 9 equations, all of them containing cross coupling. And then if we rewrite those 9 equations, we could get the form of matrix product. Occasionally, we notice that if we could multiply with the inverse of one of the matrix, we could successfully decouple those cross couplings, and only the 9 original unterminated terminal behavior model or the impedance is left. And the bottom left figure shows what we need to measure during the perturbation. After the inverse of the matrix manipulation, we could get the impedance, which correspond to the equivalent circuits for the system. So this is some theoretical show what would be the experimental stages. Firstly, we will perturb one of the model inputs at single frequency for several seconds or at least one period, and we use FFT analysis to extract the Fourier coefficients at that frequency. And because we want to perturb different frequency, perturb different model inputs, total progress will last for several minutes. In our experience, it will last around 5 minutes. And then we follow the mathematics and get the impedance we want. This simulation results in the Xinliang environment, while the blue line is still containing those couplings which we do not want. The red line is following the method, the decoupling method. The dashed line is for reference data from the datasheet. So the matching distribution of the red line and the dashed line shows the effectiveness of our theoretical deduction. And then is how we conduct the experiment. So this is our experimental setup. For the controller, we are using OPRT instead of DSP or FPGA, while the PC is always communicating with the OPRT, the hardware in the loops equipment, for signal monitoring and data collection. And always we have power amplifier from Exton playing the role of motor drive for both PMSM and induction machine, while the induction machine plays the role of mechanical load providing torque from the load side. At the same time, both machine is controlled by traditional field-oriented control. Here is some short video showing what happened during the experiment. You could see that when we perturb one of the model inputs, I believe right now we are perturbing the d-axis voltage, all of the state variables and model inputs oscillate at the same frequency. Right now, it might be 1 Hz or 3 Hz perturbation. So by this progress, we use FFT. We collect the Fourier coefficients for each of the perturbation window, and then we follow some mathematics. Here are data collection process. We only extract the Fourier coefficient at the frequency we are interested in or we perturb at. And this is the experimental result. Different from the simulation results here, the red line is relatively matched with the dashed line, not that perfect, but I think it is good enough. And we could see that at relatively higher frequency, when the frequency is more close to 100 Hz, the phase lagging or phase deviation is higher or the performance is worse. Because right now the estimation of the speed contain much more noise, so I practically reduce the bandwidth lower than just around 50 Hz. But the magnitude over frequency is always more accurate at this operating point. So by this way, we show the effectiveness of our method to extract the unterminated terminal behavior model. And also, for the procedures or the results before, we always under an assumption that the system is like a linear system at that operating point. That is some fundamentals for the method, or even transfer function, the definition of the normal transfer function based on the assumption that the system is linear time invariant system. But especially when we conduct the experiments, always due to the cable or due to the amplifier or due to the winding itself in the machine, in fact, the machine contains some phase impedance unbalance, which means, let's say one of the phase contains higher impedance or one of the phase contains smaller impedance. And when we proactively add unbalanced phase impedance in the simulation and we do FFT for one perturbation frequency, we could see that the reality is not that corresponding to LTI system assumption, but something different. For example, for a balanced machine, we could see when we perturb at single frequency for one of the model inputs, all of the in the frequency spectrum for all of the state variable or the model inputs, the dominant component is at the same frequency. So LTI system assumption is met. But for unbalanced cases, we could see not only the perturbing frequency components, but also there are 3 more dominant components. And according to our observation, we could see they are locating at the 2 times electrical frequency and 2 times plus minus perturbing frequency. And so later, what we want to do is, for unbalanced cases, we propose more generalized framework or extraction method, and also generalize the impedance definition into a cross-frequency coupling impedance. So this work, for balanced electrical machines, given the LTI system assumption, we do show that the effectiveness of our proposed method to extract the unterminated terminal behavior model still a kind of black box modeling, good for manufacturers, good for system integrators. The following up activity after the impedance extraction could be the impedance-based stability evaluation used general Nyquist stability criterion or the online controller reshaping, in other words, adaptive control or so on. And also, in the future, we want to extend the proposed method for unbalanced cases. So the so-called cross-frequency coupling under linear time periodic system dynamics assumption will be considered. Thank you. This is my presentation.